Very good evening to all respected faculty members, distinguished guests, research scholars, industry professionals, and dear students. It is my immense pleasure to welcome each one of you to this professional workshop on IoT enabled smart buildings with integrated automation. The convergence of Internet of Things, artificial intelligence, building automation systems, cloud computing, and data analytics has fundamentally changed how buildings are designed, operated, and maintained. The buildings are no longer passive physical structures, they are becoming intelligent ecosystem capable of sensing, analyzing, learning, and responding autonomously to changing environmental and human conditions. Throughout today's workshop, we shall discuss the basic fundamental concepts to advanced practical applications supported by industry case studies, automation workflows, and career opportunities. My primary objective is to ensure that every participant gains both conceptual clarity and practical insights into smart building technologies. Let us begin this exciting journey into the future of intelligent infrastructure. Before we begin our technical discussions, let us briefly understand the roadmap of today's workshop. Our learning experience has been carefully structured into five progressive stages. We shall begin with the fundamental principles of IoT and smart building architecture, establishing a strong conceptual foundation. Next, we will explore the various sensing technologies, communication protocols, and building automation systems that form the backbone of intelligent buildings. Once the concepts are clear, we shall move towards understanding automation logic, where data collected from sensors is transformed into meaningful automation actions. Following this theoretical understanding, we will enter the practical segment through hands-on session where participants will learn how sensor information can be visualized and controlled using modern IoT platforms. Finally, we shall conclude by discussing emerging career opportunities, industry expectations, certification pathways, and future research directions. By the end of today's session, every participant should possess a comprehensive understanding of how intelligent buildings operate in the real world. Let us now understand the basic importance of smart buildings. In nutshell, the construction sector accounts for nearly one third of global energy consumption, making buildings among the largest consumer of electricity worldwide. Unfortunately, many conventional buildings continue to operate inefficiently because they lack real time monitoring, adaptive control systems, and predictive maintenance capabilities. This is where IoT enabled smart buildings become more revolutionary. Smart buildings continuously monitor occupancy, indoor air quality, temperature, humidity, lighting levels, energy consumption, and equipment health. Instead of waiting for failures to occur, intelligent systems predict potential problems well in advance and automatically optimize the building operations. Numerous studies indicate that smart automation can reduce energy consumption by 20 to 30% while simultaneously improving occupant comfort and lowering operational cost. Today's organizations are increasingly investing heavily in smart architecture not only for financial benefits but also to achieve sustainability goals, environmental compliance, and enhanced workplace productivity. Let us now go through the IoT architecture of a smart building. To understand the smart buildings, we must first understand the architecture of IoT systems. The first layer is the perception layer, where sensors and actuators collect real world information. These include temperature sensors, occupancy detectors, smart meters, humid sensors, and environmental monitoring devices. The second layer is the network layer, which is responsible for transmitting data using communication technologies such as Wi Fi Next one is ZigBee. It is a low power, short range wireless mesh networking standard primarily used for smart homes and IoT devices. The next one is Building Automation Protocol. It's an open communication protocol standard used for building automation and control networks. The next thing is low power wide area network protocol designed to wirelessly connect battery operated device to the internet. Next type of communication protocol standard is message queuing telemetry transport. It is a lightweight messaging protocol designed for low power devices and low bandwidths or unstable networks. The third layer is the data and cloud layer, where information is securely stored, processed, analyzed, and integrated into building management systems and digital twin platforms. Finally, the application layer presents meaningful insights through dashboards, mobile applications, visualization tools, and intelligent automation interfaces. Information continuously flows upward from sensors to applications, while control commands travel downward to actuators, creating an intelligent feedback loop that enable autonomous decision making. Let us now discuss the core sensors and devices used for smart building infrastructure. Sensors majorly serve as the primary sensory organs of a smart building architecture. Temperature and humidity sensors regulate HVAC systems to maintain thermal comfort. Occupancy and motion sensors detect human presence, ensuring that lighting and air conditioning operate only when it is required. Air quality sensors continuously monitor carbon dioxide and volatile organic compounds, helping to maintain healthy indoor environments. Energy meters provide detailed measurements of electricity consumption across different building zones. Smart surveillance systems access control device and biometric authentication to improve safety and security. Water leakage sensors detect pipe failures before they become major maintenance problems. Each of the sensing devices contributes valuable real time information, enabling intelligent automation and resource optimization. The next module, we shall discuss the communication protocols used in building management systems. No smart building can function effectively without reliable communication protocols. Different communication protocols are designed for various operational requirements. First one is building automation protocol remains the industry standard for large commercial building management systems. ZigBee and Z-Wave are widely used for wireless lighting and sensor networks because of their low power consumption. Message queuing telemetry transport has become one of the most popular lightweight communication protocols for cloud connected IoT applications. Low power wide area network enables long range communication for battery operated devices across extensive campuses. Bluetooth low energy supports indoor positioning and wearable devices. Selecting the appropriate protocol depends upon the communication distance, data volume, power consumption, reliability, and infrastructure cost. Next thing, let us see how integrated automation functions in a more intelligent way. True intelligence emerges only when different building subsystems work together rather than independently. A modern building automation system integrates HVAC, lighting, energy management, security, fire safety, and occupant services into one unified platform. Say, for example, when occupancy sensors detect that a meeting room has become vacant, the system can automatically switch off lighting, reduce air conditioning, update room availability, and record energy savings, all without human intervention. This seamless integration significantly enhances operational efficiency while reducing energy wastage and maintenance cost. Let us see the automation logic in smart buildings. Automation follows a systematic five-stage cycle. First stage, sensors collect the basic available information. The second stage, communication gateways transmit the collected data. Third one, cloud platforms and building management systems analyze the incoming information using predefined rules or artificial intelligence. Fourth stage, actuators execute the required control actions. Finally, dashboards and mobile applications inform facility managers about system status and performance. This continuous feedback mechanism distinguishes true intelligent automation from ordinary remote monitoring systems. Let us now understand the above concepts with a case study. Examine one of the world's most celebrated example, the Edge building in Amsterdam. This remarkable office complex incorporates nearly 28,000 interconnected sensors that continuously monitor occupancy, lighting, indoor climate, park utilization, and workspace availability. Using intelligent automation, lighting adapts according to daylight availability and occupancy levels. Employees reserve workspaces using mobile applications, while renewable energy generated through rooftop solar installations contributes to sustainable operations. This project demonstrates how intelligent integration simultaneously improves energy efficiency, occupant satisfaction, operational excellence, and environmental sustainability. Let us now have a simulation video on intelligent integrated automation of smart building. Theory alone is insufficient for mastering IoT technologies. So let us have some video simulation about the practical implementation that is equally important in this workshop. So, this practical experience bridges the gap between the academic learning and industrial practices. So, followed by the simulation video, we will now continue with the remaining part of the discussion. So, student learning outcomes. By the completion of this workshop, every participant should be able to completely understand the IoT architecture, identify the appropriate sensing technologies, selection of suitable communication protocol standards, design automation workflows, analyze the smart building case studies, and relate these competencies to emerging professional roles. These outcomes prepare you for advanced academic research as well as industry oriented smart infrastructure projects. In terms of career opportunities, there is a high demand for professionals specializing in smart buildings continues to grow rapidly. Career opportunities include IoT engineer, embedded systems developer, building automation engineer, energy audit or energy analyst, facility technology manager, smart infrastructure consultant, digital twin specialist, and IoT entrepreneur. As governments worldwide promote smart cities and sustainable development, expertise in intelligent building technologies will become increasingly valuable across multiple engineering disciplines. Let us now summarize the today's key takeaways of the workshop. As we conclude the today's workshop, let us reflect upon the following key message. The smart buildings represent far more than technological advancement. They embody a vision of sustainability, operational excellence, energy efficiency, and human centric design. This integration of IoT, automation, cloud computing, and artificial intelligence is transforming the way buildings are conceived, constructed, and managed. I encourage every participant to continue exploring these technologies by undertaking practical projects, pursue relevant certification, and contribute meaningfully to the development of future intelligent infrastructure. I sincerely hope that today's workshop has inspired you to embrace innovation and lifelong learning. Thank you for your valuable participation, your thoughtful engagement, and your valuable time. I wish you every success in your academic research and professional journey. Thank you and have a wonderful day.